Okay, so we're going to look at the Asymmetric Key Encryption Lab. So you should hopefully have reviewed the material on RSA and elliptic curve methods, and this lab will give you some practical experience on those techniques. So a public key usually looks like this. So we'll see the standard header and footer here, and a base64 in the middle with a version description here. The other one we'll see is a private key. So that will say private key. The private key contains both the public key and the private key within it. And we wouldn't distribute that private key, but we can distribute the public key. The way that PGP works is that the sender will create a new symmetric key, then we'll encrypt the message in a signed hash with their private key, and that symmetric key will then be encrypted with the public key of the recipient. The recipient then uses their private key to be able to decrypt the encrypted symmetric key, and then is able to decrypt the message and the signed hash. The recipient will then use the sender's public key to verify that they were the person who sent the email. So we'll have a look at this block here, and we'll just paste it in. So you've got to watch for the new line characters. So I'll probably just copy from here. Paste in here. Okay, so if you're interested, I'm using JavaScript code here to integrate into the browser, but you can use Python and Node.js, and there we go. So we can see here is the version number, and there's an ID. So the ID has a name, so that's the name that you refer to in the for the identifier of the person, and this is the email address. There's a fingerprint that the key has, and also a hexadecimal key ID. So you can see in this case we're using RSA, and that's the RSA key here. Okay, probably 2048 bits long. Okay, so find some other public keys and see if you can actually get them read in with this page here. So the next part of the lab, what we have is a private key here, and this produces this ciphertext. So what we're going to try and do is to decrypt the ciphertext with Bob's private key. Okay, and the code we're going to use is this here. So we should be able to import RSA. We import the key here with these methods, and then we'll just use a standard decrypt to be able to decrypt the code. Okay, so we'll give this a try. So I think the code, I've already included the code. Should be this one here. Okay, so it's this one here. So what we'll do is we'll run that, and hopefully we should be able to decrypt the message. And it says, congrats, the flag is nothing is impossible. Okay, so this little bit of code allows us to be able to decrypt our RSA message. Now what we'll do is we'll use OpenSSL to generate some keys. Okay, so this should generate 1024-bit RSA keys. And that's it. So it did it extremely quickly. If we wanted to try 2048, it would probably take a bit longer to do it. So we try them. Took a little bit longer. Let's try 4096. You see it maybe took about 2 seconds there. So we'll go back and we'll look at our 1024-bit keys. And we now should have a file called private.pem. So we'll just list that. And then it's there. So this file contains our public and our private key. If we want to have a little look to see how the keys change, so we can see we have a bigger key there, and if we go for 4096-bit keys, you can see they're extremely long. But we'll go back to our 1024-bit keys. One thing to notice that the E value, if we think we have the message to the power of E mod of N, then the E value is there, which is 65,537, or it's that in hexadecimal. Okay, so we've listed our private key. Now what we'll do is we'll view it. And view in a text format. And then it's there. Right, so what we see here, there's the exponent value. There is our modulus, so that's the value of n. So that's our two prime numbers together. It gives us that value. And this is our decryption key here, our D value. The two prime numbers that we've used to generate the value of n is this prime number and this prime number. Okay, so that's how you would view the key. So if you think about it, when we encrypt, it's the message to the power of E. So the value of E is this value, mod n, which is this value. And then when we decrypt, we take the cipher and raise it to the power of D, which is this value, and then take mod of n, which is this value, and that's the way it works. The two prime numbers that we've used are here and here. So you can see here that when we multiply these together, they give a a modulus which is equal to the double the bit lengths of each prime. Okay, so these primes will be 512-bit primes to give a 1024-bit modulus. Okay, so we can secure our private key, in this case with 3 des. There we go. Okay, and I'll just call it password of Napier. Okay, so we now have encrypted our private key with a password so that no one can access it unless they know the password. So make sure your private keys have a good strong password. Now what we'll do is we'll export to our public key so that we can actually distribute it. It's in a PEM format, so that's equivalent to the format that we saw before, and it's a distributable format where we can distribute it in a text, in any text channels. So we'll try that one. Okay, so we're going to use RSA. We'll take in our private key, and we're using des to encrypt that private key. Let me copy and paste it again. Copy. That's it. Okay, so remember, RSA has 2 prime numbers that multiply together, and we take an E value and we raise the message to the power of E, and then to decrypt we take the cipher and we raise it to the power of D. Okay, so we now hopefully have our public key, and there it is there. Okay, so that's the public key which we can now export. So just like we saw in the last Python program, that's what the key actually looks like. If we want, we can encrypt our public key, and then we can now encrypt. So what we'll do is we'll create a file. We'll call it my file.txt. Okay, so I'm now going to encrypt that file with my public key. Encrypt with my public key, taking the input file and then output file. Okay, so we should find that this file is in binary because we've not converted it into base 64. So now what we'll do is we'll decrypt the file just to make sure that it's working okay. SSL RSA minus decrypt. decrypt minus key and key, private key, while the bin is our binary cipher and output there. Okay, so hopefully when we decrypt it, we get the right message back again. Okay, so that shows you an example of how we generate the keys, how we export the public key, how we can then encrypt with RSA and then decrypt with it using OpenSSL. So what we'll do is we'll now generate a key pair for our SSH keys. So SSH keys are very, very important, and they will be used to connect to cloud infrastructure and also to something like GitHub. Okay, so make sure you protect your keys. Okay, so I'll just put in Fred. Okay, so it puts it into a file in the .ssh folder, and it's going to call it ID RSA. I'll give it a passphrase, and that's it. Okay, so if we want to list our keys, or list the files that are in that folder. There they are. Okay, so we're going to have a little look at our keys. Okay, so here they are here, and what we've got is a public key, and then it's there. Okay, so that's your SSH RSA keys. I think it was 2048 bits. Is our keys there. So we'll have a look to see what our private key looks like. And then it's there. Okay, so this is our private key, and we can see here it's an encrypted key with this. This is the password which will open it up, obviously in an encrypted format. So we've taken the password and we've encrypted it, and this is it in here. So the key itself is protected when we use it. Okay, so we can now add these keys as our SSH keys. Okay, so when I use SSH now to connect, it will use my public key to identify this machine. So make sure that you protect these keys, because if anyone gets these, they could actually log into a remote site. Next, what to do is to go to GitHub and to create your own account. So within GitHub, you should, once you've created it, you should be able to go to your profile. Okay, so within GitHub, you should be able to look at your profile, and then you should be able to upload your SSH keys here. And then these will be used to identify you when you log in to GitHub. Okay, so go ahead and create your GitHub account, upload your keys, and then you'll be able to identify yourself. Then, once you create a file on GitHub, if you try and use this command, or if you use the HTTP version of this, you should be able to download the files onto your computer from GitHub. Okay, so the version that I use Okay, so here is the command that will pull the code from my GitHub. So if you do a similar one, you should be able to paste that in there. Once you've set up some files on your GitHub, then you should be able to clone it to a folder, and it should download all of the code. So the next part of the lab, what we'll do is we'll investigate elliptic curve cryptography. Okay, so let's give that a start. Okay, so we'll have a look at our private key now that it's there. So we have elliptic curve parameters such as G and the prime number that we're using, and also the elliptic curve type. So that's contained in this part here, and then as we saw, the private key contains, in this case it only contains the private key. So from the private key we can now generate the public key. So let's have a look at some of the details of our key to look at the basic parameters that are held on it. Okay, so we can see here that our parameters are, this is the prime number that we're using, and then we have y squared is equal to x cubed plus ax plus b. So in this case a is 0 and b is 7. So there's x cubed plus 7. The generator is the point, the G point on the curve. And then this is the order of the prime. So these are the basic parameters for our elliptic curve method. Then what we do is we generate the public key. based on this private key. So this will generate a random number, which will give us our public key. Okay, so there's the private key. So that's a scalar. That's the gradient from the G point. And this is our public key. This is an x, y value. So this is x value and y value are in there. And this identifies the curve, the point type. Okay, so now let's try some elliptic curve cryptography using Python. So let me go back to where I was before, and I should have some code there. Okay, so there's the code. So in this case, so we take, in this case, we generate our private key here and a public key. So this here will generate our key pair for us using the elliptic curve methods. There's the public key and the private key for Bob and Alice. We then encrypt something, so that's the word here we're going to encrypt. So encrypt it here, we create our cipher, and then we'll decrypt it. Sorry, we'll create a signature in this case, and then we'll decrypt it with the other key. Okay, so it just takes a little minute. So we've actually proven it here, where we've managed to decrypt the message. Okay, so if you have a look at the code, see if you can see how it actually works. The test, the message that we're actually encrypting is this message here. We're encrypting it with Bob's public key, and then we're decrypting it with Bob's private key. Okay, so in the next one, so this is the curve that we've just used that we saw with the elliptic curve. So this is where we have A is equal to 0 and to B is equal to 7. And we do this in terms of a prime number. So although it looks like a lovely curve, because we now bring in a prime number for our operations, then we end up with a number of points. So if we use that elliptic curve, and we'll take a prime number of 89, let's see if we can generate the first few points. And it's ECC points. Okay, so these are the first few points that we get on the elliptic curve. Okay, so continue on and try these examples here, and you should be able to build up a basic outline of this. So in the next one, what you've got to do is to be able to generate a P value and a Q value, and then go through the basics of RSA key picking. And so the best way to do this is we'll give a Python. Just try with Python. So let's pick a p-value of 3. Let's go for a q-value of 7. So n is equal to p times q. And phi is equal to p minus 1 times q minus 1. Okay, so n is that, and phi is that. We now need to pick an e value which does not share a factor with phi. So the factors of phi are 3, 2, 3, 4, 5 would work. So we can now pick a value of 5 for e. Now what we must do is to make sure that d times 5 mod of phi to 12 is equal to 1. Okay, so we could try lots of values of d to be able to find it. So we could just keep incrementing d to see if we can find the value. But what we'll do is that we'll use a method called inverse mod to be able to find that value for us quickly. Encryption inverse mod. So the inverse mod of 5 mod 12 unfortunately gives us a value of 5. So it's not a great example that we've used, but I carry on with it. So 5 times 5 is 25, mod 12 is 1. So our decryption key is 5. Okay, so then our message. So let's say we have a message of 4. And we'll take our cipher is equal to m to the power of e mod n. So 16. We're now going to decrypt that. So the, I'll just call it plain PL, is equal to c to the power of d mod n. Hopefully, fingers crossed, this will be 4. And it is. Okay, so I appreciate that the encryption key is the same as the decryption key, but it actually works. What I'll do is I'll show you another example just to make sure that it works, and hopefully we won't get the same the same encryption and decryption key. So this time I'll use 11. So where we've got 3 and 11, so we'll recalculate n. recalculate phi. We just print n, which is a modulus 33, and we'll print out phi. And we'll pick E. So E shouldn't share a factor with phi. So this time the factors are 2, 4, 5 and so on. So we'll pick 3. So now we must find D times 3 mod phi is equal to 1. And phi in this case is 20. So it's 3 into 20. And the result is 7. Okay, so here we go again. Cipher is equal to the message to the power of E mod n. And the plain text, or the deciphered value is equal to the cipher to the power of D mod n. Now, as if by magic, the result should be 4. Oops, it's not, because I did that a bit wrong. Okay, it should be mod n. Mod n. Okay, and as if by magic, then the result should be 4, and it is. Okay, so that's how RSA actually works. Okay, so we can run a little simple Python program to just do what we did there. It's extremely simple. It's not using the complex method that we saw there. But let's see if we can run it through here. Nope, it's broken our line spacings. But if you try this code, it should actually work for simple examples. Okay, so this was the code that we used here. So see how you get on with that one. In this part, what we'd like you to do is to be able to create our PGP encryption key, or GPG. So the first thing that you do is to enter your command to generate the keys. So I've already generated my keys. GPG minus list keys. Sometimes you need to do sudo to list your keys. Okay, so I've already imported a key here from someone, and these are my keys. So I have my private key on my keyring and my public key, and then I'll add public keys from people that I would send emails to onto my keyring. So once you receive your a key, then you should be able to import it. So if you want, you can use my public key here. So you would import that into your keyring, export your public key, and then if you want to send someone, you want someone to send you an encrypted email, you would send them your public key. You then import that onto your keyring with this command here, then list them. If you want to encrypt, you encrypt with your name, and then you give the name of the person that you want to encrypt with the name of the file. What they should receive is this ASC file. So I should have an example here. Okay, so this is a message that's been sent to me from someone whose public key I've put in my keyring. So then after I receive this, I just run the -decrypt on the file. Into my private key. I can remember it. And it gives me the decrypted file there. Okay, so if you can create two accounts or dummy accounts that you could send from one to the other, then that's great. If not, if you send me an encrypted email, I'll try and decrypt it and send it back. So with this last part here, what we're going to use is TrueCrypt, which is a disk encryption method. So it creates a file that can be mounted as a folder. With this, we use a passphrase and some salt to generate the key, which will open up the encryption key which is used on the disk. So if you could, TrueCrypt is installed on a Linux Kali machine. So if you run that, and then what we'll do is we'll create a volume. We'll do a little test on benchmarking of the encryption method. We'll mount it as a drive, and then what we'll do is we'll download these TrueCrypt volumes and see if you can open them up with these passwords. Let's see if it's opened up yet. So after this, we'll use TrueCrack to be able to create a list of passwords and see if we can open up the volume. So we could easily install it into any Linux or Windows machine, but it's just pre-installed onto Linux Kali. So we'll run it from here. Okay, so we've got a number of slots that we can create. So we'll create a volume, create a container, standard volume, we'll do a little benchmark to see how well the encryption methods run. So we want to pick an efficient method. So in this case, we can see that AES is very fast. We can also use AES with 2FISH to give double encryption and so on. Okay, but we'll go for that. And there's the hashing method that we use. And unfortunately, I don't have any free space on the disk just now. Just let me see. Just select a file. And it's up to yourself what you want to make the size of the file. So I'll just make it 10 megabytes. And so this will be the password which will open up the encrypted file. Make it FAT so it can be mounted onto Windows, and it's creating a random number for us. And that's it. Okay, so we can now mount that onto there. Okay. And there it's there. Okay, so I'll now put file onto there. And that's it. Okay, so what we can do is we can dismount that and it'll be there as a file. We can then, if we have a USB drive, we can take that encrypted drive off, because it's basically just a file. And then if we want to open up again, we'll have to put in the password again. Okay, so there's the encrypted drive there. That has just one file in it just now. I could take that off and put it onto a Windows machine and open that up from there. Okay, so that just shows you an example of TrueCrypt. Then with the TrueCrack, we create a words list. So we'll add in our words that we're going to use. And then we can use TrueCrack to be able to crack the password or the encryption key that's on the disk. Okay, so that's been an outline of the lab.